So first I will give a brief about the previous lectures. We have talked about in the previous lecture the use of CFD, what is CFD, and the application of CFD, and what are the processes of CFD. So in the following slides, we will introduce you to the discretization methods, how we will discretize governing equations, and then we will show you the higher order discretization. So in fact, the discretization is the crux of CFD, in which we replace the derivative terms by some equivalent formula. So if you have a domain like this, and by discretization we means breaking up this whole domain into the small parts, and into the small parts can be called control volume. So all of the domain are broken into a finite set of control volumes, which in the CFD terminology are called mesh or grid. So on all these control volumes or the mesh cells, the convection general conservation equations are solved. So let us have a look on the general conservation equation in a condensed form, del by dt of rho phi dv, and like this. So this is a very condensed form of the general conservation transport equations. There is a unsteady term, there is a convective term, there is a diffusive terms, and there can be a generation term. So in this equation, if we put value of phi 1, then we will get a continuity equation, and if we introduce u in place of phi, we will get x momentum equations, and if we introduce enthalpy or energy in place of phi, we will get an energy equations. So the general conservation equations have these terms, and all of these terms behave in a very different manner. So whenever we will discretize an equations, we will take care of these terms and apply the appropriate choice of discretization to these terms. Because these terms behave in a different manner, the unsteady terms will be discretized on a time basis, and the convection terms have a non-linearity, second order non-linearity. So it may have upwind discretization, and diffusion may have a similar other scheme of discretization, like diffusion process, because uh, is isotropic, so a central scheme can be used. So we will talk about the upwind scheme and central scheme in the forthcoming lectures. So basically there are three types of method to discretize our governing equations. The first is finite difference method, in which we replace the derivative terms by its algebraic equivalent. The finite difference method are very easy to code, very easy to implement, and they have excellent accuracy. But they are usually used for Cartesian coordinates, and in some case we can modify the equations by transformation, and then can we apply the finite difference method on curved surface also. The second one is finite volume method, which is the most widely used, and it is at the heart of the commercial softwares, because it is applicable to a wide variety of flow problems and wide variety of geometries. And the third is finite element method. In finite element method, we discretize the whole domain into elements, and the variation between the elements is considered. The finite value element method is more flexible when it comes to complex geometry. However, it is more suitable for the solid structure because in fluid flow problems, boundary layer forms and the finite element cells compress inside the boundary layer, because near the boundary layer we have to refine the mesh and we have to cluster the cell. So we have to compress the finite element cells. Because of that, the distortion can take place. So though the finite element method is can be applied to any complex geometry, but it has slightly less accuracy in comparison to the finite volume method. And the finite difference methods have highest accuracy, but it can be only applied to simple flow problems which have easy geometry. So now we will talk more about finite difference in this whole course, because it is very easy to understand, very easy to code. So what is the method of finite difference? So as I told you, the crux of the finite difference method is to replace derivative with some algebraic formulations. So to have a better understanding of it, let us say that we have a function fx which is behaving like this, and its derivative del f by del x is x can be geometrically attributed to a slope of a line, uh, this line AB, right? So the true derivative or the true value of del f by del x is the slope of this line. What we do in finite difference, we discretize this whole line into many parts, and we have some nodes, for example x naught, plus del x and x naught minus del x. So now geometrically we can calculate the derivative connecting this point and this point by this formula. Later on we will show that how this formula can come from Taylor series. So right now we are agreed that we can calculate the derivative of this line using this point and this point by this formula. So what if this del x distance, which is the distance between these 2 points, uh, becomes infinitely small. So when this distance will become infinitesimally small, this point will coincide with this point, and this approximation of derivative will be equivalent to this true derivative. So in a similar manner, the derivative at this point can be approximated by using this point and this point. So this derivative, the slope of this line can be calculated and it can be replaced with the true derivative. So once again, if the distance between these 2 points becomes infinitesimally smaller, the approximate derivatives del f by del x will converge to the value of true derivative. So this is the meaning of discretization as far as the finite difference method is concerned. So we can build up several formula for this del f by del x. We can use this point and this point. We can use this point and this point. So when using a forward point, it will be called forward differencing or forward approximation. And when using a backward point to approximate the derivative, it will be called backward approximation or backward finite difference. And we can also use this point and this point, which are at the left and right of the main point x naught, at which we are calculating the value of the derivative. So basically in finite differences, the partial differential equations are replaced by a system of algebraic equation. So every derivative terms can be replaced by some algebraic form as shown in previous slide. So the whatever solution we will get only at only discrete points. So entire domain can be split up like this. If it is a one-dimensional domain, we can say that this entire domain is split between n minus 1 cells or n minus 1 parts. So if you want to calculate the derivative at here, so we can use this point and this I plus 1 point. We can use this I plus 1 point, this point I plus 2 and this point also. So we can construct as much as formulas for derivatives equivalent as we want. So as I told you earlier that if this spacing del x uh, in the continuum limit when this spacing approaches to 0, so our approximations which I have shown you in the previous slide will converge to the partial differential equations. And similarly, we can discretize del f by del t, like we have discretized the del f by del x, and in the continuum limit, when the del x approaches to 0 and del t approaches to 0, our finite difference equivalent will return to their partial differential form. And as I have earlier told you that discrete derivatives are not unique. What is the meaning of it? That if you want to calculate the derivative at this point, we can construct as many as formula for the derivative of this point. So we can use both these points. We can use 3 points at the right side and 1 point at the left side, and we can use 2 point right side and 2 point I minus 1 and I minus 2 at the left side, and we can construct del f by del x equivalent. So as much as the information or the number of nodes are included in calculating the equivalent of del f by del x, the accuracy will increase. We will show you later that how the accuracy increase by including more and more points. So this structure is called stencil. And stencil means how on many points we have used and what is the strategy to use points in your finite difference approximation. So if you use more number of points, your approximation will be more accurate. So if you use 1 point for del f by del x, it is called first order accurate. Use 2 points, it may be called second order accurate. We will show you that how the accuracy vary with the number of points. So basically the question is how can we derive this finite difference equivalent. So there is a method which is more popular than any other method, which are called Taylor series expansions. So all the finite difference equivalents can be calculated by Taylor series expansion and doing some algebra. So if you know Taylor series, we have this function fx, and the value of this function fx in the neighborhood can be obtained by Taylor series expansion. So what is the value of the function fx plus delta x? It will be equivalent to fx plus del f by del x into del x 1 by 2 factorial del 2f by del x2 del x power 2 and so on. So this is the Taylor series expansion of fx in the neighborhood of del x. So if we calculate the fx plus del x, this series will go to infinity, and the more number of these points are included in the calculations, more will the accurate will be this approximation. So based on the strategy of finite differencing, our strategy can be called forward differences, backward difference, central difference. So now from here we will denote in index terms the expansion of Taylor series. I will stand for x direction and the j is the index for y directions. So here we have a function f which varies accordingly, and at the I we want to calculate the gradient del f by del x, and there is a point neighborhood point I plus 1 and there is a backward point I minus 1. So if we expand Taylor series around x I plus 1, I mean this point, then by the Taylor series xi plus 1 can be written as fxi del f by del x, xi minus xi, xi plus 1 minus xi square by 2 factorial, and so on. So this difference is called mesh spacing or mesh size. So it can be uniform, it can be non-uniform, we will see it later. So in this Taylor series expansion, if we uh, let us uh, let us ignore this term. So if we neglect this whole term, then we are left with this much terms. And after rearranging, we want to calculate del f by del x. We can get del f by del x at I location as fx plus I minus fxi divided by xi plus 1 minus xi. So where fxi plus 1 is the value of the function f at location I plus 1 and fxi is the value of the function at location I divided by del x I plus 1. So if we consider that del xi plus 1 is equal to xi plus 1 minus xi, and if this is uniform, it means I xi plus 1 minus xi is equivalent to xi minus 1 minus xi. It means the spacing between the 2 points are same, then it is called uniform mesh or uniform grid. So in a similar manner, if we uh, expand fxi minus 1, I mean using backward point to the I, which is I minus 1, we can get this Taylor series. And once again, we will neglect the higher order terms, and by manipulating these terms, we want to calculate del f by del x at I location, we will get this formula. So this is a different formula from the previous formula. So in that formula, xi and xi plus 1 was used. In this formula, xi and xi minus 1 is used. So this is called backward difference or backward approximation of the derivative at location xi. So in a similar manner, we can calculate this del f by del x at I using I minus 1 and I plus 1. And in this formula, we are not using the point xi. So we can say that del f by del x comes to this, and we can easily get it by by taking subtraction of the forward difference formula to the backward difference formula. And again, in this process, we will neglect higher order term. So if we consider that the mesh spacing is or the distance between two nodes is uniform or constant, then we can call the grid is uniform. So in this case, the forward differences can be written as this, and backward differences can be written as this, and the central difference is can be written as this. So basically there are three formula for approximating the derivative of f at location I. You can generate as much as formula as you want. So there will be some truncation error because we have neglected the higher order terms. The leading terms in the truncated series and the power of del x will cover the truncation error. If the power of del x in the truncated or neglected series is 1, then the finite difference will be set to first order accurate. And if the power of del x in the neglected truncated series is 2, then the finite difference equivalent will be set to second order accurate. So we can uh, fastly move to an example where how can we calculate the value of x at its neighborhood. So this is the Taylor series, and there is a function fx is equal to sine 2 pi del x, and at x equal to zero point 0.2 we know the value of fx, and if you want to calculate the value of f at 0.22 by Taylor series, then del x will be suppose 0.02. So from equivalent formula neglecting higher order terms, we can write that fx plus delta x equal to fx plus del f by del x into del x. So fx plus delta x is the value of the function at 0.22, and the value of the function at x we know, derivative we know, del x we know, and this can be calculated as this much. While we can directly calculate the value of the function at this by putting the value of x 0.22, the actual solution will be 0.9823, which gives error 0.775%. And if we use more terms in the Taylor series, like we include these terms also in calculating the fx plus del x, then the error will goes down. So this was a simple explanation of truncation error and order of accuracy. So if we use this terms and this term also in our calculation, then it will be called second order accurate solution. So using Taylor series, we can also derive the second order derivatives formula. So if we similarly use the Taylor series expansion around I plus 1 and I minus 1 and add those expansion, the many terms will be cancelled out, and we can equate del 2f by del x2 to this plus some higher order terms. So formula for del 2f by del x2 will be fi plus 1 minus 2fi plus fi minus 1 divided by del x square plus higher order terms which are of the order of the del x. Similarly, you can calculate forward difference second order forward difference formula for second order derivative, in which all the forward point to the I will be used, that is I plus 1 and I plus 2. Similarly, you can get the backward formula. Keep also in mind that this is again first order accurate, and this is second order accurate. In a similar manner, we can also expand Taylor series for calculating the mixed derivative. So fx plus del x, y plus del y will goes like this, and again we can calculate the central difference, forward difference, and backward difference. So we don't need to go in details of this. So these are the questions for practice. Deriving a finite difference forward formula for second order derivative using more than 3 points, and derive a backward differentiation formula of the second order derivative by using 3 points. References. Thank you.